So synthetic division is a shortcut or a fake way to do long division. You can only use it when you have a binomial where a is equal to 1. Anything else, you got to still use long division. With synthetic division, we have no variables and no exponents, and make sure that you have a placeholder if you're ever missing one. So our highest degree is 2, then we have a degree 1, and then we have x to the 0 power. So we have all of our placeholders. So we start by taking our coefficients, which are 2, 1, and negative 10. We have them set up 2, 1, and negative 10. And then we have the opposite of our factor or our solution, our root, which will go right here in this kind of backwards L. Synthetic division is kind of fast. The steps are you drop the first number. After you drop the first number, you're going to multiply the number down here with the number in the backwards L. We get 4. Then you're going to add those two together and you get 5. Then you're going to multiply again the 5 and then whatever number's in that backwards L. We get 10. We'll add those together and we get 0. So we have our remainder is always in the last spot. So we have a remainder here of 0. We have our coefficient of a 2 and then a 5. Since our term started out as highest degree x squared and we just divided out an x, we drop our degree by 1 and then we combine the rest of our pieces together. So final answer would be 2x plus 5, and that divides evenly into the polynomial 2x squared plus x minus 10. Some things to point out in the next example, it is not set up in standard form. So make sure that before you do example number 2, that you switch those two, put them in standard form, and then divide. Please go try that. I'll show you the answer for that one now. So here there was a remainder of 3. We dropped down all of our pieces. Don't forget to add on your remainder divided by your divisor. And the last one, you had some placeholders missing. So make sure you fill in your placeholders first. And then again, pause the video, go try it, and make sure that you can do long division. Okay, if you need a full video, it's in the first video with long division. So feel free to go and watch that. So the real lesson today is, well, the second part of the lesson is on the remainder theorem. The remainder theorem says if a possible 0 is divided into the polynomial and the remainder is 0, then the possible 0 is a 0. So this means like possible solution is divided into the polynomial and the remainder is the number 0, then that solution of 0 is a actual solution. Okay, so let me show what that looks like. So one way that you could solve this is you could take x is 2 and you could plug it in using function notation. That gives you f of 2, which is then 2 to the third minus 4 times 2 squared, then plus 5 times 2 plus 3. And you could go and you could solve this. So you could get out your calculator, you could plug it all in and solve it. And if you would do that, you would get 5. Oops. So what our remainder theorem says is if you would use division and divide, so they're giving us that solution, so we're going to put it in, that 0. I can set up synthetic division. I can do synthetic division, drop 1, multiply by 2, add, we get negative 2, we multiply, add, multiply, and add, that this remainder would be the same as the answer to that function. Okay, so you could just use the remainder theorem to solve. So if I want to know what is f of negative 4, I could do synthetic division. We get a remainder of negative 151. So therefore, f of negative 4 is equal to negative 151. I'm going to use a lot of synthetic division. We have another theorem. We actually have 3 theorems in this unit, but the second one is called the factor theorem. And the factor theorem is pretty logical. It says that x plus a is a factor if f of that solution is equal to 0. So if we have a factor and we solve and we get a remainder of 0, then we know that that factor is a 0. Now, information can be given to you in 2 different ways. It can be given to you, what the heck is this? It can be given to you that the information is a factor, like in this first one, it's giving you x minus 3. Where in the second example here, they're giving you -1 is a 0. So those are 2 sides of opposite sides of the same coin, I think is the saying. I don't know. So this, they're giving you it as a factor. Here, they're giving you it as a 0. So when you're doing synthetic division, if they're giving you a factor, you have to use the opposite sign or the 0 when you plug it in to that backwards L. Okay? So this first question is asking you to use synthetic division to show that x minus 3 is a factor of the polynomial. And we're going to use the result to factor the polynomial completely. Then we'll list all the zeros. So if we can take this 3rd degree polynomial down to a quadratic by factoring out, then the results give us, we can get to our zeros. So I'm just doing synthetic division. I got 0. That means that x minus 3 is a factor. So we have x minus 3 as a factor. Then we also have 2x squared minus 3x minus 2. That's just coming from these coefficients using synthetic division. Okay, from here, we have a quadratic, so we can factor that. I can use the British method. So British method says we start by multiplying a and c together. So we multiply, we get -4. The numbers that add to -3, the middle number, and multiply to -4 would be 4 and -1. This part a lot of people are forgetting to do of splitting our middle piece into those terms. So 4x and -1. And then the first term and the last term come down. Now we're going to factor by grouping. So we'll split it. We take out a 2x, we get x plus 2. Take out a -1, still have x plus 2. We double check to make sure that I have identical parentheses. So I have x plus 2 and x plus 2. And then we commute or move to our final answer. So we factor out a GCF of x plus 2, and then we get 2x minus 1. So in fully factored form, this polynomial is x minus 3, 2x minus 1, and then x plus 2. So by knowing one of the factors in the original polynomial, we were able to take this polynomial, divide out this factor, and then we were given this, we had this quadratic, and we know how to solve quadratics because we've been doing that all school year. From here, we have 3 factors, so I can take each factor, and then I can solve it. So x is equal to 3, x is equal to 1/2, x is equal to -2. I'm taking these factors and I'm setting them equal to 0, solving them just like we did with quadratics. In the second example, they're giving us the 0. So the factor would be x plus 1. The 0 is -1. And when we use synthetic division, we use the 0. So I'm going to put the -1 in. We got 15, 14, -3, and -2. because we know that it's a 0, I should get a remainder of 0. Which we do. So then we have our factor, x plus 1. We have our quadratic. And now we need to factor our quadratic. So again, I have to do the British method. So I have 15x squared minus 1x minus 2. So the first thing that we do is we multiply. When we multiply, we get negative 30. The numbers that are going to multiply to negative 30 and at the same time add to negative 1 would be negative 6 and positive 5. So we set up factor by grouping. It's my dog snoring in the background. I don't know if you can hear her. We get, 5x. That leaves me with 3x plus 1 and negative 2, 3x plus 1. We have identical parentheses, which we always check for. They are both 3x plus 1. They should always match. And then we are going to move to our final answer, or commute. And we have 5x minus 2, 3x plus 1. And remember, those can go in either order. So now we have our three factors. We have x plus 1, we have 5x minus 2, and we also have 3x plus 1. Set those equal to 0, and then we can solve each factor. So x is equal to negative 1, x is equal to 2/5, and x is equal to 1/3. Negative 1/3. I'll rewrite that. And just like we have been doing when we would go to graph those would be let's see, 2/5 would be like here. That would be where our polynomials cross that x-axis, and then we could use our end behavior, knowing that we would go up, down, and then up. Okay. You could use your calculator to find out where that relative max and relative min are, but this connects directly to what we were doing in the second part of this unit. We're just building up to the rational root theorem, which we'll do in class next time I see you.